Electrochemistry, Part 3, the Redox reaction. Predicting of redox reaction. We know that the redox reaction is a reaction between the acceptor and donor. The acceptor is the oxidant, the donor is the reductant, and the particle exchanged is the electron. So no reaction between oxidant 1 and oxidant 2, and no reaction between reductants. To know the direction of the redox reaction, we put the couples on increasing order of the potential E. On the left, we put the oxidant, which is the acceptor, and on the left, we put the reductant, which is the donor of the particle electron. Then we determine the species present. According to this scale, the reaction between OX2 and Red1 takes place, and this reaction is advanced since it's in direction gamma. The redox reaction may be limited, advanced, quantitative, or complete, depending on the value of alpha, so depending on the K of the reaction. Since most of the redox reaction does not have the stoichiometry 111, so the value Kr greater than 10 to the power 6, which is the quantitativity of the reaction, could not be applied in this case. So to avoid the calculation of the condition of quantitativity for the redox reaction, we will suppose if K of the reaction is very high, so the reaction is complete, or we can say K of the reaction is very low, so the reaction is limited. In case we have a mixture containing several oxidants and several reductants, the dominant reaction is between the strongest oxidant and the strongest reductant. And in case we have several reactions possible, we can apply the rules of the sequence. For example, if two reactions are possible and they have the same stoichiometry, we can compare the value of K. If K of reaction 1 is 100 times greater than K of reaction 2, so the reaction 1 starts, ends, then reaction 2 starts. The spontaneity of redox reaction. To know if a reaction is spontaneous according to thermodynamics, we can calculate delta G of the reaction, and if delta G of the reaction is negative, so the reaction is spontaneous. Spontaneous means that it takes place in the condition mentioned. And if we want to know if a reaction is advanced, limited, quantitative, or complete, we can calculate the value of Kr, which is related to delta G0. So delta G is the spontaneity of the reaction, and delta G0 is the advancement of the reaction. In the electrochemical cell or in the electrochemical reaction, we measure the potential difference, and the unit is volt. So we measure the difference in potential energy between the reactants and products. So we calculate what we call the EMF or the electromotive force, which is the potential difference in volt and is equal to the work of the reaction divided by the charge. And since the work is done by the system in thermodynamics, it's indicated by the sign minus. So E of the cell is equal the work minus W divided by the charge Q. So the work W equal minus Q E of the cell, or equal minus Q E of the reaction. So E of the cell or E of the reaction is the potential difference at which that current flowed. Q is the charge in coulombs transferred. The charge of 1 mole of electron is constant and called the Faraday noted F, which is equal to 96485 coulomb per mole of electron. So Q is equal to the number of electrons times the Faraday constant. Combining W equal minus Q of the cell and Q equal NF, we obtain the relation delta G equal minus NF E of the reaction, and to note that at P and T constant, the W is equal to delta G. So now we have a relation between delta G and E of the reaction. If delta G is negative, the reaction is spontaneous. That means E of the reaction is positive. And if delta G is positive or E of the reaction is negative, the reaction is not spontaneous. So in electrochemistry, to know if a redox reaction is spontaneous or not, we can calculate E of this reaction. And to note that E of the reaction is the potential difference between the couples or between the reactant and the product. So if E of the reaction is positive, that means this redox reaction is spontaneous, or E of the reaction is negative, the reaction is non-spontaneous. On the spontaneity of redox reaction, consider the following redox reaction. Is it spontaneous or not? So the first step is to divide the global reaction into half reactions. We have Cu2 plus that is transformed to Cu plus 2 electrons, and Fe transformed to Fe2 plus minus 2 electrons. So the first is a reduction, and E0 at the cathode is equal 0.34 volt, which is E0 of the kappa Cu2 plus Cu, and E0 at the anode equal minus 0.44 volt. The second step is to calculate E of the cell, which is equal E0 reduction minus E0 oxidation. So E0 of the cell is equal 0.78 volt. Since E of the cell is positive, so this reaction is spontaneous. To note that E of the cell in this example is E0 of the cell, since all data given are at the standard state. Another application, predict if 1 molar HNO3 nitric acid can dissolve gold metal to form a solution of gold 1 molar. So nitrate is transformed to NO and plus 3 electrons. This is a reduction. E0 equal 0.96 volt, and E0 are given, E0 values. and the gold is transformed to AU3 plus, and we lose 3 electrons. This is oxidation, so E0 at the anode equal plus 1.5. E of the cell equal E0 cathode minus E0 anode. So E0 of the cell, which is equal E of the cell in this case, equal minus 0.54 volt. E of the cell is negative, so this reaction is non-spontaneous, and nitric acid cannot attack or dissolve gold metal. Between E0 of the cell, delta G0, and K. To note that E0 of the cell, or the standard potential of the reaction, is equal E0 cathode minus E0 anode. Delta G0 of the reaction is the standard free enthalpy. K is the equilibrium constant of the reaction. E0 of the cell is related to delta G0 of the reaction, so E0 of the cell is an indication about the advancement of the reaction. E of the cell is different from E0 of the cell, and E of the cell is related to delta G of the reaction, so E of the cell is an indication about the spontaneity of the reaction. In thermodynamics, delta G equal delta G0 plus RT ln Q. Delta G is the free enthalpy, delta G0 the standard free enthalpy, and the Q is the thermodynamic ratio. At equilibrium, delta G equals 0, so delta G0 equal minus RT ln Q. We have this famous triangle, which is the relation between delta G0, E0 of the cell, and K. Delta G0 of the reaction or of the cell equal minus NF E0 of the cell. Delta G0 is related to K. Delta G0 equal minus RT ln K. So what is the relation between E0 of the cell and the equilibrium constant? Delta G0 equal minus NF E0 of the cell, so minus RT ln Q equal minus NF E0 of the cell. So E0 of the cell equal RT divided by NF ln Q, and at 25 degree, we transform the ln to log, so E0 of the cell is equal 0.0592 divided by N log K, or simply K equal 10 to the power N E0 of the cell divided by 0.0592. So what would be the cell potential when the concentration of ions are not equal to 1 molar, or in other words, what would be the cell potential if we are not at the standard state? Consider the following reaction between zinc and Cu2 plus to give zinc 2 plus and Cu. At the standard state, when using concentration of zinc 2 plus and Cu2 plus equal 1 molar, we observe that E0 of the cell is equal to 1.10. What would be the cell potential if we restart the same galvanic cell by using zinc 2 plus equal 0.01 molar and Cu2 plus equal 2 molar? When the concentrations in the beakers are not equal to 1 molar, so we are not at the standard state. So this value of the difference of potential could not be written E0 of the cell. So we noted E of the cell. According to Le Chatelier principle, In the second figure, the zinc 2 plus concentration decrease and we increase the concentration of Cu2 plus. So according to Le Chatelier principle, decreasing zinc 2 plus and or increasing Cu2 plus will shift the equilibrium in direction 1, in the forward direction, so it will increase the driving force of the electrons and therefore the cell potential E of the cell will increase, and that what was observed. So for any galvanic cell which is not at the standard state, it has a value E of the cell and a value of E0 of the cell. And E of the cell is variable, E0 of the cell is constant. And E of the cell is related to E0 of the cell. Relation between E and E0. Delta G is equal delta G0 plus RT ln Q. And delta G is related to E of the cell. Delta G0 is related to E0 of the cell. So minus NFE equal minus NFE0 plus RT ln Q divided by NF, we obtain E of the cell or E of the reaction equal E0 of the reaction minus RT divided by NF ln Q. R is the ideal gas constant equal 8.314 joule mole minus 1 Kelvin minus 1. T is the temperature in Kelvin. N is the number of moles exchanged in the reaction. F is the Faraday constant. And the Q is the thermodynamic ratio. To note, for solid we use the value 1. For ions we use concentrations. And for gas, we use pressure. Remember that N must be the number of moles of electron transferred in the balanced equation and not in the couple. For the process to which we apply this equation that is called the Nernst equation. Using this relation, we can calculate the potential of the cell in which some or all of the components are not in their standard states. Since ln equal 2.3 log, so this relation is transformed to E equal E0 minus RT divided by NF times 2.3 log Q. At T equal 25 degree 298 Kelvin, we put R by its value and F, which is the Faraday constant 96465, and the relation is transformed to E of the reaction equal E0 of the reaction minus 0.0592 divided by N log Q. So for the general reaction, A plus B plus an electron to C plus D, we can apply E of the cell equal E0 of the cell minus 0.0592 divided by N, and N is the number of electrons exchanged in course of the reaction, log Q, Q is equal to the thermodynamic ratio. Use Nernst relation to calculate the potential of the electrode. Consider the half reaction of reduction. Ox plus N electron gives red. Nernst equation is E equal E0 minus RT divided by NF ln Q, and the Q is the ratio between the product and the reactants. So we apply this relation directly on the half reaction, implies E oxrad equal E0 oxrad minus RT divided by NF ln product rad divided by the ox. Pay attention, in this relation, we have to use the sequence ox-rad, ox-rad, and N is the number of electrons exchanged in the couple. In the Nernst relation for the reaction, the value of N was the number of electrons exchanged in the reaction. So in this case is the number of electrons exchanged in the couple. So E oxrad equal E0 oxrad plus RT divided by NF log ox divided by rad. In some books, they prefer to use the first minus, so rad divided by ox, and in other books, they use plus, so it's the relation between ox divided by rad. R is the ideal gas constant, T the temperature in Kelvin, N is the number of electrons exchanged in the half reaction, so in the couple, and F is Faraday constant. So by the same way, this relation at 25 degrees is E oxrad equal E0 oxrad minus 0.0592 divided by N log rad divided by ox, or E oxrad equal E0 oxrad plus 0.0592 divided by N log ox over rad. The application of Nernst relation for the calculation of the potential of electrode, consider the couple Cu2 plus Cu. We write the reduction have reaction Cu2 plus 2 electrons give Cu. We apply E oxrad, so E Cu2 plus Cu equal E0 Cu2 plus Cu minus RT divided by NF ln product. So in the product we have solid, we put the value 1 divided by the concentration of Cu2 plus, or at 25 degrees we apply directly the relation E Cu2 plus Cu equal E0 Cu2 plus Cu minus 0.0592 divided by the number of electron exchange in the couple 2 log 1 over Cu2 plus. Another couple is HgCl2 Hg, E HgCl2 Hg equal E0 in the sequence oxrad minus RT divided by NF ln product. For Hg we put the value 1, for Cl minus, so Cl minus square divided by 1 because HgCl2 is solid, or at 25 degrees equal E0 minus 0.0592 divided by 2 log Cl minus square. For the couple Cl2 to Cl minus, we apply Nernst equation E oxrad, so E Cl2 Cl minus equal E0 Cl2 Cl minus minus RT divided by NF ln product, so Cl minus square divided by the pressure of Cl2 since Cl2 is gas. E at 25 degrees E Cl2 Cl minus equal E0 Cl2 Cl minus minus 0.0592 divided by 2 log Cl minus square divided by PCl2. More complicated couple is the couple dichromate chromium. So E oxrad, this is chromium 3 plus, E Cr2O7 2 minus Cr3 plus equal E0 oxrad minus RT divided by NF ln product. So Cr3 plus square H2O, we put value 1, liquid, divided by reactant Cr2O7 2 minus concentration times HCO plus concentrations to the power 14. So E oxrad equal E0 oxrad minus 0.0592 divided by the number of electron exchange in the couple, which is 6 log chromium 3 plus square divided by dichromate concentration times HCO plus to the power 14. So the potential of the couple dichromate chromium 3 plus depends on the concentration of HCO plus used. So we have a relation between E and the pH of the solution. Polyoxidants ampholyte solution. Some elements can exist in several oxidation states, and they can play the role of oxidant in a couple and the role of reductant in other couple. For example, vanadium exists in many oxidation states 2, 3, 4, and 5. So vanadium, we have 3 couples, vanadium 5, vanadium 4, vanadium 4, vanadium 3, vanadium 3, and vanadium 2. We may have, for example, another couple, vanadium 5, vanadium 2, vanadium 4, vanadium 2. So if we choose only these 3 couples, vanadium 5 and vanadium 4, vanadium 3 play the role of oxidant. Vanadium 4, vanadium 3, vanadium 2 play the role of reductant. But vanadium 4 is reductant in a couple and oxidant in another couple, so it's ampholyte, and this is also the case of vanadium 3. Calculation of the electrode potential of a couple from other couples of the same family. For example, when dissolving CuSO4 in solution, the species present are Cu2 plus, SO4 minus obtained by the direct dissolution of CuSO4, then Cu2 plus may be transformed to Cu, or Cu2 plus transformed to Cu plus. So the species present are Cu2 plus, Cu plus, Cu, and SO4 2 minus. According to the arrangement of the couple of increasing order of potential E, the couple Cu2 plus, Cu plus, Cu has E greater than Cu2 plus, Cu plus. And Cu plus is oxidant in a couple and reductant in other couple, so Cu plus is ampholyte. But according to the gamma rule, Cu2 plus react with itself, the other Cu plus, to give Cu2 plus and Cu. In this case, Cu plus is unstable and it cannot exist in solution. We talk about this mutation of Cu plus or disproportionation of Cu plus. Consider the 2 couples Cu2 plus, Cu plus, and Cu plus, Cu. Find the potential of the couple Cu2 plus, Cu. Cu2 plus, Cu. Cu2 plus is oxidant and Cu is reductant, so Cu2 plus Cu can form a couple. We write the half reactions. Cu2 plus 1 electron gives Cu plus. This is the corresponding half reaction of the couple Cu2 plus Cu. Delta G01 of this half reaction equal minus N1 F E0, 1 of the reaction, and N1 is equal to 1. For the couple Cu plus Cu, we write the half reaction Cu plus 1 electron gives Cu. Delta G02 for this half reaction equal minus N2, and N2 in this case is also equal 1, F E02. For the couple Cu2 plus Cu, we write the half reaction Cu2 plus 2 electron gives Cu, and delta G03 equal minus N3 Fe03, and N3 in this case is equal to note that we want to find E03. In thermodynamics, we know that delta G is a function state, so delta G of the global reaction is equal to the sum or the combination of delta G of other reactions. So delta G03 is the global reaction of reaction 1 and 2. So delta G03 equal delta G01 plus delta G02. Therefore, N3F E30 equal N1F E10 plus N2F E20. Therefore, E03 equal N1 E01 plus N2 E02 divided by N3. To note that this relation can be applied directly without doing this proof. But we have to pay attention for the sequence of the couples. We know Cu2 plus to Cu plus, it's E0. For example, it's E0, 1, and the number of electron exchange is N1. We know from Cu plus to Cu, the potential is E02, and the number of electron exchange is N2. So from Cu2 plus to Cu, it's E03, and the number of electron exchange is N3. So we can apply in this case this relation without the proof. We can say E03 equal N1 E01 plus N2 E02 divided by N3. Domain of predominance of ox and red of the same couple. In the acid base, the predominance domain of the donor HA and the acceptor A- depends on the pH of the solution. In electrochemistry, the domain of predominance of the oxidant and its reductant depends on the value of the potential of the solution. Example, consider a solution of Fe2 plus and Fe3 plus, where the concentration of these two species in the solution is 1 molar. Fe2 plus can be transformed to Fe3 plus and vice versa, but the sum of their concentrations is always equal 1 molar in this example. So the electrode potential depends on the concentration of the oxidant in the solution and the reductant in solution. So E of the couple FeC plus Fe2 plus equal E0 of the couple FeC plus Fe2 plus 0.0592 divided by N, which is equal 1. Here we use 1, so we have to put ox over red and not red over ox. So equal E0 plus 0.0592 divided by 1 log FeC plus divided by Fe2 plus in the solution. If FeC plus predominates on Fe2 plus, that means its concentration is at least 10 times greater. So in this case, E of the solution, which is equal to E of the couple, should be greater than E0 plus 0.0592. And if Fe2 plus predominates on FeC plus, Fe2 plus should be greater at least 10 times FeC plus. So the potential of the couple or the potential of the solution is less than E0 minus 0.0592. So in the scale on E of the solution, if the potential of the solution or the potential of the couple is less than E0 minus 0.0592, so the reductant is predominant. And if E of the solution is greater than E0 plus 0.0592, so the oxidant is reductant. For a potential of E of the solution between E0 minus 0.0592 and E0 plus 0.0592, the ox and the reductant codominate. This is the same analogy used in the acid base. If pH is less than pKa minus 1, the acid predominate, which is the donor. Here, if E of the solution is less than E0 minus 0.0592, so the red predominate. And the same for the oxidant domain and the base domain. To note that this domain can change from a couple to another couple. Here we obtain E0 plus 0.0592 since the number of electron exchange is 1. For another couple with number of exchange different than 1, the interval, the domain of predominance would be changed. Concentration cell. Because cell potentials depend on the concentration, so we can construct galvanic cell where both compartments contain the same components but at different concentrations. In this figure of galvanic cell, we have the same couple in the two beakers, which is Cu2 plus Cu. But in the first, we use Cu2 plus concentration different from that in the second. And as we know that according to Nernst equation, the potential of the couple Cu2 plus Cu in each beaker is equal E0 Cu2 plus Cu plus 0.0592 divided by N, which is equal to log concentration of the Cu2 plus. The two couples have the same E0 Cu2 plus Cu, but E Cu2 plus Cu in beaker 1 is different from E Cu2 plus Cu in beaker 2 since the concentration of Cu2 plus is different. So as Cu2 plus increase, E Cu2 plus Cu will increase. And since the concentration of Cu2 plus in beaker 2 is equal to molar greater than that in beaker 1, so the couple on the right, Cu2 plus Cu, has a potential E greater than E of the couple Cu2 plus Cu on the left side. So when the cell concentrations are different, the electrons flow from the anode to the cathode, so from the solution which is less concentrated to that which is more concentrated. And when the cell concentrations are equal, at this stage, E of the cell will be equal to 0 and E of the couples will be equal. To note that when the reaction starts, E anode will increase and E cathode will decrease. So at a certain level, we will have E cathode equal E anode and E of the cell will be equal to 0. It's possible, so it's possible as a conclusion, it's possible to get a spontaneous reaction when the oxidation and the reduction reaction are the same as long as the electrolyte concentrations are different. In this example, E0 of the cell is equal to 0 since the two couples have the same value of E0 of the couple, but E of the cell is different from 0, and in this example is equal 0.068. The cell notation is Cu solid, Cu plus 0.01, salt bridge, Cu2 plus 2 molar, then Cu solid, or W latter. So the reaction, the global reaction taking place is Cu1 plus Cu2 plus 2 gives Cu2 plus Cu2 plus 1. As a direct example, consider the galvanic cell composed of the couple Ni2 plus Ni, where the concentration in the first beaker is 10 minus 3 and in the second is 1 molar. Even we have the same couples, E of the cell is different from 0 since we have different concentrations of Ni2 plus. The flow of the electron will continue till the equilibrium where E of the cell is equal to 0. So when E of the couples are equal. At the anode, we have oxidation, so Ni transformed to Ni2 plus 2 electron. At the cathode, we have reduction, Ni2 plus 2 electron gives Ni, and the global reaction Ni1 plus Ni2 plus 2 give Ni2 plus Ni2 plus 1. So E at the anode equal E of the couple Ni2 plus Ni equal E0 Ni2 plus Ni minus 0.0592 divided by the number of electron exchanged 2 log 1 over Ni2 plus at the anode. So the value of E at the anode is equal minus 0.36 volt. At the cathode, we have the same relation of Nernst equation, but the concentration is different, which is equal to 1 molar, so the value is equal minus 0.28 volt. E0 of the cell at the anode is equal to E0 of the cell at the cathode, so E0 of the cell is equal to 0. But E of the cell is equal E cathode minus E anode minus 0.28 minus 0.37 is equal 0.09 volt. At equilibrium, E of couple 1 is equal E of the couple 2, and since they have the same equation of Nernst, so that means the concentrations of Ni2 plus in the beaker 1 and beaker 2 should be equal. So the concentration of Ni2 plus at equilibrium is equal to the concentration of Ni2 plus at equilibrium in the anode and the cathode is equal to 1 plus 0.01 divided by 2, so the concentration is approximately 0.5 molar.